In the last class, we were discussing about this typical FPGA board, which is Spartan of Xilinx. So, where here is a FPGA chip, and around that you have got the I/O pads, the LEDs here, and there are a number of switches here. You have got a display, and you can have many other auxiliary chips also on the FPGA development kit. Spartan is one. Similarly, there are other starter kits or other kits on which you can develop. Now, this kit has got a number of interfaces whose layout is not known to the FPGA itself. So, you have to explicitly establish a connection between the FPGA CLVs and the I/O ports. When we do the programming, yesterday last class we were talking about some programming, which is in the form of programming the interconnects. So, in that we will show how we design the configuration bits, but for complex circuits it will not be possible to do it in the way that we are doing in the class. So, here is just as a recapitulation. Here is a typical FPGA structure, where you have got a number of configurable logic blocks, and the interconnects can be programmed using the switch boxes, and each of these switch boxes is like a crossbar switch with the array of the interconnects, and I can establish the connections in between them using two types of possible technology for establishing the interconnects. One is the antifuse, another is the SRAM based. So, antifuse based interconnections are permanent, and SRAM based interconnects are programmable. Therefore, we can program that also in different ways. This we did in the last class. So, here is again what we did last time, that if we take a look at a simple CLB configurable logic block, inside that it can be even more complex than this, but this is a simple one where we have got a lookup table and a D flip flop and a mux. So, the input will come as the input of the lookup table, and from this lookup table will be programmed with the configuration bits, and based on the input one particular location of the lookup table will be activated, and we will take that output, and that output will be fed at the mux. Now, depending on how I configure the mux or whatever control signal I give to the mux, either the input that is coming directly from the lookup table or the output that is coming from the flip flop. This input is also coming at the input of the D flip flop. So, depending on my desire, I can either select this input or this input to come to the output. Therefore, my programming will not only include programming this lookup table, but will also include programming the selection bit or bits of the mux. Here it is only one bit that is required, because I have got only two inputs and I have to select from one of them. Now, if I select through the D flip flop, then obviously I am getting a state concept here. I can get it at the next clock, I can come to this, right. Thereby, because of the presence of such D flip flops, if you think a little bit, you will be able to see that I can also combine the number of CLBs to make a register or a shift register for that matter. A shift register, each bit of a shift register is nothing but a flip flop, right. So, I can create an interconnect of that. Now, we were doing a very simple implementation. What was that was a 4 input AND gate, and the approach that we adopted is writing down the truth table of the AND gate. The 4 inputs are coming at the input of the lookup table, of course, through the address decoder. All right. The outputs are being fed here. The output is being programmed into the lookup table, and depending on whatever the input is, any one of those bits will come out at the output, right. So, if the input is 0, 1, 1, 0, so this will select a particular location from here, which is programmed to be 0, that will come here, and I also program the mux to select the first input, the top input. Therefore, this is also 0, and hence whatever is coming out from here will come out as the output. Thereby, I can implement a 4 input AND gate using this. That was a very simple design by programming one particular CLB. Here only one CLB has been used, and that CLB has been programmed as an 4 input AND gate. Okay. Next, we also discussed about the interconnection network and how we establish the interconnect. In the programmable scenario, the interconnects are being established using pass transistors, right. These are the pass transistors. So, I have got, my papers are gone there. So, I can draw it again. So, I have got 4 points, 2 wires are coming. I can either establish the signal to flow in this direction, or in this direction, or in this direction, or in this direction, etc. So, there are 6 possibilities, right. So, with something like this, once again I repeat, I have got 2 wires. So, I can make the signal flow in this direction or in this direction, it may be in this direction, or it can flow diagonally from here to here like that. So, I have got 4 points A, B, C, D. I can either come from A to B, B to C, C to D, A to D or whatever, or A to C or B to D. Therefore, any one of these 6 lines can need to be shorted. So, for that, for each of these lines are connected to a pass transistor, where if I put a 1, then this pass transistor will be conducting, therefore, it will flow like this, and if I put a 0, this will not be conducting. Therefore, if I take this example now, you can see that I have written a 1 here, that means this pass transistor will be on, others will be off. Therefore, any signal coming through this path will flow to this path, right. So, in that way, any switch box I can program by using this pass transistor gate bits. This is a transistor and this is a signal that we are giving at the gate of the transistor. So, depending on the programming of the gate bit, I can program the interconnect also. Because of this programmability, FPGA actually is called a programmable gate array. Okay. Now, let us take another example. I think we did up to this in the last class. So, let us take another example. So, we have to establish a program. We have to write a program to implement a particular logic circuit, okay, or particular logic. So, here is an example, a second example. Determine the configuration bits for the following circuit. Implementation will be done in a 2 by 2 FPGA with IO constraints as shown in the following figure. We assume that there are 2 input LUTs in each CLB. All right. Which circuit? This is what is there in, this is a circuit that I want to do. All right. Now, we have already seen what is there in one CLB. In one CLB, we have got a lookup table and a D flip flop and a mux. So, that is my basic unit. Using that, I have to implement an AND gate which is coming to the D flip flop, and another is the output, another input is coming at an XOR gate, and I will get the output. So, this is what I want to achieve using the 2 input lookup tables. Now, lookup tables, the lookup table that I had shown earlier did not have any restriction on this. Here I am saying that there are 2 input lookup tables. So, how can I implement this? If I break this up into 2 let us work it out. So, there are 2 components of this circuit, right, this and this, and I need 2 CLBs. I am achieving 2 CLBs. Of course, you could have said that, well, I will make a, you could have said that, well, I will make a truth table of the whole thing, and I could do it with 1 lookup table, right. But here I am showing, I am intentionally doing it with 2 CLBs to show you how the programming is done. So, suppose this part input 1 and input 2 goes to the D flip flop, and I will take the output from the D flip flop. That will be my, that will be implemented using CLB 1, and the CLB 2 will simply implement the XOR gate, where one input is coming from the output of the D flip flop of the previous stage, and the other one will come from the third input. Okay. Now, here is the programming that we have done. Just look at this, simple. What I am trying to do is an AND gate here, nothing else. An AND gate will be 2 input AND gates, everything 0 except for 1 input. When the input is 1, so that will come out through this. But my desire in this example is, unlike the previous one, I will take the output through the D flip flop. So, 1 state later, that is my specification. Therefore, unlike the earlier case of 4 input AND gate, here I have to program the multiplexer with a 1. So, that this is not selected, instead this one is selected, right. So, this part's programming, the configuration bits will be 0 0 0 1 and multiplexer will be 1. So, this programming will yield this circuit. Again, coming to this circuit, here I have to implement just the XOR gate, and the XOR gate can be implemented using the truth table 0 1 1 0, because it will be 1 only when not A and B, or sorry, not A or B and A not B, all right. So, either one of them will be true, both of them cannot be 1 or both of them cannot be 0. So, I take out this, but here the output is directly coming out. Therefore, from this lookup table, again I program the lookup table according to the logic that I want to have here, and I program the multiplexer to have a 0, because I want this output to be propagated to the actual output. This is the actual output. Clear? Is it okay? So, and what will be the input of this lookup table? The input of this lookup table will be the output of this and the third input. This input should come here. So, once I decide on this design that I will select 2 CLBs and I will implement this part with this CLB, this part with this CLB. The next part that will be required is selecting the CLBs on the FPGA array. So, you see, this is the programming. I have done some allocation here, allocation of the tasks to two different CLBs, but where should those CLBs will be placed? Now, if I come here and say I decide that my two inputs will be coming here. There are three inputs in my desired circuit. Input 1 and input 2 will be coming here. Input 3 will come to this CLB. Okay. And I can take the output directly from here, or suppose I want to take the output from here, from this CLB, just for the sake of it. Okay. I could have taken it also from here. Then my interconnections. So, this is the first of all placement. This is not so trivial the way I said. It is if it be a complicated circuit with a number of logic elements, then your placement is also important, because there is some delay involved in each of these propagations, these switch boxes, going through the switch boxes and all those, and also the area is very important. I cannot arbitrarily go on putting in the logic functions on the CLBs. We need some optimization for that. But just for the sake of example, if I decide that there are two functions, two CLBs we decided to work with, and this was one and this was another, this function and this function, I say decide that this one will go to CLB 0 and the other one, this one, will come to CLB 2. Then I have to establish an interconnection between them. Okay. Now, how do I establish an interconnection between them? That will be through this switch box 1, and let us have a quick look at the switch box 1. I want the current to flow from in this direction, right, not through this, not in this direction, not in any other direction, but in this direction. So, therefore, this pass transistor, which is connecting node A and D, say A, B, C, D, A and C, that should be 1, all others will be 0. Agreed? Similarly, if I want to propagate the output that is being generated from here to this, I have to select the SB4, switch box 4, and program it so that this path is activated. Now, if I had taken the output from this CLB, of course, this switch box would not be needed at all. That is also very well done. I mean, I can do it in this way. First of all, therefore, I want to program these two inputs and the output coming to this CLB. So, in order to achieve that, what are the two things that I have to program? Just for the first one, the CLB 0 has to be programmed and SB1 has to be programmed. What should be the program of CLB 0? What should be the program of CLB 0? We have already seen CLB 0 will be implementing this AND gate. Therefore, it will be 0, 0, 0, 1, right, and the multiplexer should be 1. So, 0, 0, 0, 1, 1, that will be the programming of the CLB 0. And that is also known as the configuration bits of that I have to program for CLB 0. 0, 0, 0, 1, this much was coming from the lookup table and 1 for the multiplexer, right. That is the CLB 0. And what do I need in which switch box am I needing here? I am needing switch box 1. So, switch box 1 will require only this to be 1 and all others to be 0. Therefore, the switch box 1 will be all zeros except this particular bit to be 1. That is the programming of the switch box 1. On the other hand, these switch boxes are not active. So, they are all zeros, you can see switch box 0, switch box 2, switch box 3 are all 0.
Connections are listed in a sequence of switch box connections 0, 0, 0.
Yes, of course, that there is some convention. I mean, at the end I will show how you can establish those connections, but each of these bits, each of the bits in this configurable this configuration bits are referring to one particular pass transistor position in the case of switch box. In the case of CLBs, it is of course the lookup table and the inputs, right. Now, so far so fine. So, if I want to have the CLB2, that is this logic circuit implemented, in CLB2, then what would be my programming bits? 0, 1, 1, 0 and 0, 0, 1, 1, 0 and 0 for the multiplexer. So, that should go for the CLB programming here. So, CLB2 will be programmed as 0, 1, 1, 0. Actually, for CLB1 which I am not using, CLB1, CLB3 I am not using, I really do not care what I am giving here. Okay. What is there in the lookup table, that is not of concern to me for this particular purpose. Okay. Now, so for that CLB2, for the CLB2, I wanted to have the multiplexer control to be 0 and 0, 1, 1, 0 to be the lookup table inputs. Accordingly, CLB2 you have got 0, 1, 1, 0 and 0 for the multiplexer, fine. Now, to make the things complicated, I have decided that well, I will take the output not from this CLB, I will take the output from this CLB. That puts me in a spot, because now this output that was coming out from this CLB has to be propagated to this and will come out from here. So, how can I do that? Now, this switch box will have to be programmed so that the connection is established in this direction, right. And for that I have to make this bit to be 1 and all other bits to be 0. That is quite visible here. Only this bit to be 1, all other bits will have to be 0, right. So, accordingly, again if I go to the configuration bits, switch box 4, it is switch box 4, right. So, switch box 4 will have all these zeros and only 1 to be 1. Now, what will happen to this CLB? Data will come from here and will come out from here without any transformation. So, what should it be? How should I program this CLB? Absolutely, absolutely. I can do that with a simple AND gate with 1 to be 1 and whatever is coming as the output will go out here, right. So, my truth table will be that of an AND gate, 2 input AND gate 0 0 0 1 1 0 1 1, all right, and the outputs will be all zeros and this to be 1. So, that is what I will put in the CLB, and this will come to the D flip flop as well as directly, and it will come to a mux, right. So, what would be the control for the mux here? It should be 0. So, my programming for this will be 0 0 0 1 0. These AND gate information coming from here and this mux information coming from here, right. That will be the configuration for the CLB3. Just a minute. So, here I had shown that the CLB3 what it would be. So, you have already found out. Yes, for CLB2 the mux was 0, because CLB2 is just giving the output from here, and I am just taking this output at the input of CLB3. So, this is coming through the switch box. Okay. So, this is an example, and I just had added this part so that you work out what the logic will be. So, based on this we can implement the circuit that was given, this circuit can be implemented using, this would be my program, these will be the configuration bits. Of course, this has to be filled up with the patterns of zeros and ones as we have found out. So, this is something that we loaded on that FPGA board, so that the logic is implemented. Now, one thing is that this input 1, input 2, now I would recommend all of you to try your hands on different FPGA boards, whatever is available in your hardware lab or in any other lab. If you get access to different Xilinx or Actel FPGAs, now each of them, now for Xilinx or Actel again there are different varieties of the kits, right. So, for each of the kits there is a different configuration. The configuration that I had shown, we had shown, they will have a Xilinx FPGA, but what are there around it, that is one important issue. You will have to adapt, you have to know that, and accordingly you have to do that. Now, this arriving at this programming is achieved by using some programming tools. Every FPGA platform comes with development systems where ISEs, all right, where you can put in Verilog or VHDL code, and they will convert it in the form of a FPGA program, and this FPGA program is nothing but an array of such configuration bits, and those configuration bits are uploaded into the FPGA memory, and accordingly the interconnects are established and the whole thing will start working. Now, along with that programming you need two things. One is the high level code that you give and you compile, and that will be uploaded on the FPGA. Also there is a user constraint file, UCF. That file, I will just show it to you later, that file has to be created, so that these inputs, which this input 1 is connected to which input pin, this output 1 is connected to which output pin, you are to decide that and you can establish. So, how are you getting this placement? One thing is that if the entire thing is automated, everything will be placed and you do not have to do anything, and often that is suboptimal. So, sometimes we would like to do it ourselves. So, thereby you can establish the interconnection using writing that particular file. Okay. Now, this FPGA that or CLB that we are showing was rather simplistic. So, but it is easier to understand, we need not unnecessarily complicate it, but here you can see this is a relatively realistic FPGA CLB, where it is again from Xilinx. You have got 3 logic units, all right, and then a bunch of multiplexers and 2 D flip flops, right, and each of them are 4 inputs. You can see you can also connect. So, here from the experience they have decided that okay, I will have the facility of implementing logic functions in a much more efficient way. If I have got 3 lookup tables, each 4 inputs, I can use them, or I may not like to use them, and a bunch of these multiplexers and D flip flops. Okay. This is a relatively realistic situation of an FPGA, of a CLB in an FPGA, right. Next, although we will not discuss the languages VHDL or Verilog in detail in the class, and I ask all of you, there are a lot of reference materials for VHDL and Verilog, and you can very well, there are even on the internet there are several tutorials. You should go through those tutorials and learn it. Now, today I will just simply talk about some parts, some salient parts of VHDL and utilize it to show you how we can have a simple toy problem solved with an FPGA using VHDL. Okay. So, you know that HDL is hardware description language, and VHDL has been developed for VLSI hardware description language, and it can be used for synthesis as well as for simulation. Now, it can be at different levels. I can describe a circuit. We will talk about that later when we talk about modeling, but usually we can, again, if you remember that Geiski's Y chart, you will remember that we can have a behavioral description, what it does, structural description. So, I can describe a circuit or a design intent, what I want a circuit to do, using either in the behavioral level or at the structural level. Okay. Today, let us start with some descriptions of the behavioral level. Say, I have got some entity, whatever that is, some behavior B, which will have, say, some inputs and some output. So, this is an entity. We describe that as an entity. Okay. An entity is associated with the inputs and the output, which we call ports. All right. So, these are the ports, this and this, these are the ports of this entity. Now, let us say I want to design a half adder. What will be the inputs of the half adder? Say I say X, one bit, Y is another bit, and maybe I will put in an enable signal. And what will be the outputs of the half adder? All of you know that it will be carry and the sum of the result, right. Now, this is an entity, half adder is an entity. So, in VHDL, I can describe this as entity. I can give a name to this, half adder is. Now, these are keywords, right? Entity half adder is, then inside this I will describe this half adder. How can it be described? It can be described with ports. So, I have got port. What are the ports here? X, Y and enable. These are ports which are input ports and of type bit, whereas carry and result are output ports and this is also bit. Okay. I am sorry, I have to complete this bracket. So, that is my port description. Now, if I just look at, I do not look at this, I just look at this description and I want to redraw something. So, I can redraw this. Suppose this is not shown to me, I can just look at it and redraw it, that okay, there is an entity and its name is half adder, and it has got X, Y and enable ports, are ports and each of them are input ports and these are bits, and carry and result are output ports and these are also of type bits. Now, as soon as by looking at this I take it out and you can see that these two are absolutely equivalent, this one and this one, right. Now, here before we conclude today, we will continue with this. VHDL, just like in C language we have got some standard library functions, VHDL always includes library which is IEEE library. So, we include library IEEE for before the entity declaration. Now, this library uses some and also another library which is known as STD logic, standard logic. There is another library. Now, these libraries are included. The standard logic is required in order to establish the interconnections. Now, you can see that we had taken the liberty of defining these things, bit, in, out. What are these? Now, bit is a standard logic type, bit, one bit, that is known a priori, we need not define those. Similarly, if there be, suppose I want to define a say 4 bits, I just want to say 4 bits coming here, say that is suppose some output, I can say output to be 4 bits where 3, 2, 0, that means 0, 1, 2, 3, 4 bits, this output is 4 bits output. Okay. We will see those in the next class. So, therefore, I can either have bit or I can have an array of bits, all right. So, there are different data types and all those which we will see in the next class. We will not do the VHDL in its entirety, but we will just do some parts and work out an exercise of an FPGA programming using VHDL. Okay.